Chapter 5, Information Technology and Moore's Law. The history of computing started in the 60s. First, we had large, room-sized computers. Next came mini-computers that were the size of a refrigerator. Finally, personal computers were introduced, which took computing from large organizations to the individual. Now that computing devices are broadly available, the next wave was access to data through the Internet. Currently, we see the implementation of the Internet of Things, where multiple devices in our lives are connected. Computers consist of four components: the central processing unit, or CPU, data memory and storage that can be short or long term, along with input and output devices. Computers come in a variety of form factors, including personal computer desktops, laptops, workstations, handhelds, and tablets. We also have smaller devices, including PDAs, phones, and smartwatches. Business and government operations run larger and more powerful servers and supercomputers. Finally, distributed architectures have enabled grid computing, where smaller computers work together to handle larger tasks. Data storage within a computer comes in two major categories. Primary cache includes RAM, or random access memory, and ROM, or read-only memory. Secondary storage includes magnetic disk hard drives and optical disks like CDs and DVDs, with which you are probably familiar. Larger organizations also use magnetic tape, typically for data backup, along with network solutions including direct attached storage, network attached storage, and storage area networks. Data storage is measured in bytes. 1 kilobyte is 1024 bytes. 1 megabyte is 1,048,576 bytes. 1 gigabyte is over a billion bytes, and 1 terabyte is over a trillion bytes, and so on. The smallest logical block of data storage is the bit. It is based on transistors or switches. A bit is 0 or 1, off or on, and is formally base 2 or binary. The next level up is the byte, which is a string of 8 bits. 000, 00000 through 111, 111, 11 represent the decimals 0 through 255. For example, the space character is decimal 32, or binary 001, 00000. Also, the uppercase letter B is decimal 66, and binary 01, 00, 00, 10, while the lowercase letter b is decimal 98, and binary 011, 00, 010. You can find lists of decimal and binary equivalents. There are also standard functions within Microsoft Excel that can convert these values. We are used to using numbers 0 to 9. This is the decimal system. Let's review decimal numbers by starting with a 4-digit decimal number. For example, we know that 8352 is made up of 8,350 and 2. The number is broken down as shown here. But we also know that 1,000 is 10 to the third power, 100 is 10 to the second power, 10 is 10 to the first power, and 1 is 10 to the 0 power. Remember that any number to the 0 power equals 1. Next, let's look at binary numbers. Let's start with a 4-digit binary number like 1011. We recall that a byte has 8 bits, so this is a 4-character or 4-bit number, so it would be half of a byte. We can convert this binary number to decimal. Just like the decimal number 8352 in the previous slide, each binary digit represents a power of 2. The first digit 1 is multiplied by 2 to the third power, or 8. The next digit 0 is multiplied by 2 to the second power, or 4. The third digit 1 is multiplied by 2 to the first power, or 2. And the last digit 1 is multiplied by 2 to the 0 power, or 1. We add up the results and see that 1011 in binary is equivalent to 11 in decimal. Just remember there are 10 kinds of people in the world: those who understand binary and those who don't. Think about it. We saw a few examples earlier, but here's a more complete chart showing the various prefixes indicating the various number of bytes. For example, 1 trillion bytes is a terabyte, or capital T, capital B. The next evolution of computer hardware will include multi-core processors where a CPU can perform multiple tasks, along with continued growth of supercomputers. We will see continued growth of grid computing along with parallel computing. These technologies will continue to evolve as our computing needs increase in the future. One issue with all of this change is the creation of waste and the associated environmental impact. Computer components use a number of rare elements for their fabrication. These elements include lead and cadmium, which can have a major safety and environmental impact. A holistic view must be taken to ensure the availability of IT systems. This includes the hardware and application software, systems software, utility software, and data management software. All of the pieces must be working in harmony for the IT systems to function appropriately. Equally important are the network devices and software that tie all the pieces together with high availability that is secure. Finally, the team of IT professionals that makes all of this happen must be highly trained with regular updates to stay current with the fast-paced evolution of the technology. This includes both badged employees and hired third-party contractors and consultants. This evolution in the technology includes a wide variety of changes. In the hardware space alone, we have seen a number of changes. Technology convergence occurs when devices designed to do one thing start to take on the characteristics of others. For example, cell phones started as simply phones but have become mobile computers. Nanotechnology is creating smaller and smaller computers, some so small that they can be swallowed. Edge computing moves data processing to the edge of a cloud network, improving reliability, speed, and functionality. Autonomic computers manage themselves based on higher level rules. Virtualization enables one device to act like a number of different devices. On one PC, I could have multiple virtual machines running a variety of different operating systems. I can even set up a network within a single PC. Multi-core processors are single CPUs with duplicate cores that run in parallel, making the computer function as if it had multiple CPUs. Cloud computing is a web architecture that enables users to take advantage of capability out on the web. This includes application use, data storage, and other capabilities. Embedded systems are hardware devices with embedded software. Examples include digital watches, hybrid vehicles, and avionics. Moore's Law was created by Intel's Gordon Moore in 1965. He stated that transistor density on integrated circuits doubles about every 2 years. This law has been found to be fairly accurate. There are other computing elements that act in a similar manner, like the power and speed of computing power, PC memory, data storage requirements, and telecommunication speed. This connection makes sense since they are all related to the performance of electronic components. Here's a graph showing the growth of optical data communication speeds, data volumes, and transistor densities, the original Moore's Law. Note the incredible growth of each. Here we see a graph of transistor density over time. The vertical axis shows the number of transistors per microprocessor. Note that this scale is logarithmic, so the annual doubling appears to follow a straight line. Here's another example of Moore's Law in action. Here we see a semiconductor wafer. Each small square highlighted in red will become a CPU. Note that we are well past 1 trillion transistors per CPU. Imagine how small each transistor must be. We see some old-time transistors by comparison. Is there a limit to Moore's Law? many believe that the laws of physics represent a real barrier. This is known as Moore's Wall. The limits are created by the limits of technology, heat, and power. New technologies, materials, and methods are being applied to continue the growth. Other approaches include a leap in capability through the use of quantum computing, molecular computing, and the use of light to carry signals instead of electrons. Each of these is a broad topic in and of itself. That concludes this discussion. Next we review software and Chapter 13.